Hello folks, my name is Tim and welcome back to my channel. So in today's video we're going to be continuing our exploration of the ESP8266 chip and using it to Wi-Fi enable our Raspberry Pi Pico. But before we begin, I need to clarify something about this board here. Now, I bought a pack of these from a vendor advertising them as being Esp01 boards. They arrived and I began experimenting with them. Things seemed to go pretty well, so I went ahead and made my video. Unfortunately, whilst reading and experimenting in preparation for this video though, I've come to the realization that these are actually Esp01S boards, or more likely they're Esp01S clones, as they don't feature the usual text that you see in illustrations online. Now, this came as a complete surprise to me. Maybe the vendor's listing was wrong, or perhaps the wrong boards were sent out, who knows. Either way, I've ended up with Esp01S boards and not the regular Esp01 boards that I was expecting. I guess the lesson here is when buying cheap components from Amazon, eBay, AliExpress or wherever you choose to get them from, it's best to double check what actually arrives because you might be in for a bit of a surprise. Now the Esp01S is basically a drop-in replacement. An upgrade, in fact, for the regular Esp01, but it has two main differences. Firstly, it has a little bit more flash memory on board, but if you don't need the extra space, then this doesn't really matter. However, the second difference is more important. The O1S has built-in pull-up resistors on the reset and chip enable or chip PD pins, as these pins need to be pulled high for the ESP8266 chip, that's the chip that these things are built around, to work normally. Now, from reading online, I gather the regular O1 does not have these, so you need to ensure those pins are pulled high yourself, and this is normally accomplished by connecting a resistor between the appropriate pin and the 3.3 volt supply as shown. Regrettably, I don't have any regular O1 boards to demonstrate this with, so today we will continue with our S variant here, but I'll call out any adjustments you may need to make if you're using a regular O1. Okay, with that having been said, let's move on to the content of today's video. Well, last time we learned how to flash the ESP01 with custom software and how to hook up the UART interface. We then learned how to send data across it, and that wasn't a bad start. But today we're going to refine that software into something much more useful, and we're also going to be looking at the ESP8266 chip's sleep modes, so that should be quite interesting. Now, in its normal mode, this ESP8266 is relatively power hungry, especially when actively transmitting over Wi-Fi, and if you're running your application off of a battery, well, that might be a problem. However, the chip supports several sleep modes that turn off various features of the ESP8266 and thus save quite a lot of power. The lowest power mode available is Deep Sleep. But if we want to use Deep Sleep with an Esp01 or O1S variant, then we have a problem. Because although we can put the chip to sleep, we can't actually wake it back up again. This is because when activating Deep Sleep, we can either tell the ESP8266 that we want it to sleep forever, or we can tell it that we want it to sleep for some given amount of time. In both cases, the chip will enter Deep Sleep mode and it will stay there until it detects a rising edge on its reset pin. That is, until the pin changes from the low state to the high state. When this happens, the chip wakes back up and can carry on with normal operations. Now, in the timed sleep mode, the chip will actually send this wake-up signal on one of its own I/O pins. And of course, if that pin is tied to reset, then the chip will wake itself back up. Unfortunately, that particular pin isn't broken out on the Esp01 or O1S variant, so we can't make use of that wake-up mechanism, at least not without doing some very fiddly soldering. However, we do have a solution. And that's our Pico here. Since it knows when we want to communicate, it can wake the ESP8266 chip up for us, wait for it to become ready, do whatever communications we need, and then put it back to sleep again. Now, to make this work, we're going to need to adjust our circuit here. First, we need to connect the Esp01 reset pin to one of the Pico's GPIO pins, and that's going to allow the Pico to trigger the reset. I'm going to use GPIO pin number 2 here for no better reason than it's physically closest to the UART pins that we've already wired up last time. Okay, so that's all there is to that. So the next thing we need to know is when the ESP8266 has woken back up from its deep sleep and been able to reconnect to the Wi-Fi network, so it's basically ready to use again. The simplest way to do that is to connect another of our Pico's GPIO pins to one of the two GPIO pins provided by the Esp01, or the S variant in this case. And here I'm going to connect the next available GPIO pin on the Pico, and that's GPIO pin number 3, to the first GPIO pin on the Esp01. This connection will serve as a status signal. In our new software, we'll have the Esp01 here pull that pin high once it establishes a wireless connection. And then, just before it goes to sleep, we'll set it low again. The Pico can then just test this pin in order to know the state of the Esp01. Pretty simple. So, our final circuit layout ends up looking like this. First of all, we obviously need to provide the 3.3 volt supply for our Esp01, and that's coming from an external bench supply. Next, we have a connection between GPIO pin 0 on the Raspberry Pi Pico, that's the UART transmission pin on the Pico side, to the UART receiving pin on the Esp01. Following that, we have a similar connection, but in the other direction, and this is coming from the UART transmit pin of the Esp01 and connecting back to the UART receiving pin of the Raspberry Pi Pico. After that, well, both boards share a common ground connection. The next connection goes from GPIO pin number 2 on the Pico to the reset pin on the Esp01, and this connection will allow us to wake the Esp01 up from its deep sleep mode. Finally, we have a connection on GPIO pin number 3 on the Raspberry Pi Pico side to GPIO pin number 2 on the Esp01 side, and that's going to be our status indicator. This is the pin that the Raspberry Pi Pico will be able to test in order to tell if the Esp01 is available, i.e. powered up and online. Okay, so that's all there is to it if you're using an Esp01S variant like I have here. However, if you're using a regular Esp01, the non-S variant, then there's one more piece that you need to add, and that's a connection between the chip enable or chip PD pin and the 3.3 volt supply. And this is used to pull that pin high in order for the ESP8266 to run in its normal operating mode. Now, this is usually done by connecting a resistor between the appropriate pins, and I've seen values of around 100k used online, but there seems to be a lot of variety here. So full disclosure, because I don't actually have a regular non-S variant Esp01 board to test with, I haven't been able to try out this alternative circuit. If anybody does give this a go though, please leave a comment because I'd be very interested to know how you get on. Right, so that's all there is to the hardware side of things. Let's take a look at the software that these boards are now going to run. Since this has become more complicated than the simple demo we created last time, I'm going to start by going over things at a higher level before we take a look at the code. So first, the ESP and the Pico work together by passing messages over the UART. A message consists of 3 identifier bytes, MSG, and that's followed by 4 bytes of binary data holding an unsigned 32-bit integer. This tells us how large the message body is and thus how many bytes we need to read from the UART in total. Now there are 2 types of messages that we can send. The sleep message just contains the word sleep, and it's used to put the Esp01 into its deep sleep mode. Anything that isn't a sleep message is considered to be a URL that the Esp01 will make a HTTP GET request to and send back a message containing the response. Next, let's take a look at the 4 main interactions between these 2 boards. First we have the startup sequence, and this is performed when the Esp01 first powers on or when it wakes from deep sleep. The Pico just enters a wait loop, checking the value of our status GPIO pin, while the Esp01 powers up and connects to Wi-Fi. Once this is finished, it sets the status line high and the Pico can continue. To make a GET request, the Pico constructs and sends a message containing the target URL. The Esp01 reads that from the UART and makes the request. The Pico at this point is just waiting for a response, though it could be doing something more useful if there was some other work to be getting on with. The Esp01 now packages up the response and sends it over to the Pico. The sequence for a sleep message is a little bit different, and it looks like this. First the Pico sends the message, but the Esp01 this time just sends back OK before setting the status indicator low and then entering deep sleep, and it'll stay in this state until we wake it up with the Pico. So to wake it up, the Pico first sets the reset pin low and then back high, and this creates the rising edge trigger that will wake up the Esp01. The rest of this interaction is exactly the same as the startup sequence. The Pico just waits for the Esp01 to indicate that it's back online again. So with that understanding in place, let's take a look at the source code for our software here. And I'm going to begin with the Esp01 side. So our setup function here, well, that's basically just the initialization interaction that we looked at. We set our status pin low to tell the Raspberry Pi Pico that we're not available. We then initialize our wireless connection and wait for it to become ready. And after that, we set our status pin high. And this tells the Pico that we are now ready to do some work. The next method down, well, that's this send function here. This isn't particularly interesting, it just takes whatever was passed in as the variable data and wraps it up in that message format that we described. So it begins MSG, then it has the 4 bytes of binary data for the length of the message, and finally it has the body of the message. Now the only interesting part of this method is actually this little call here, and this is host to network long. Now when you send multi-byte binary data between two computer systems, you need to be aware of the byte ordering or endianness that those systems have. If you send from a big endian system to a little endian system, or vice versa, then the order of bytes will actually appear flipped on the receiver compared to the sender. And obviously if you flip those bytes, well, you end up with a very different binary value as a result. So to get around this problem, what you do is you convert from whatever your native local endianness is to an agreed convention called network byte ordering or network endianness. And that's what this function does. And of course there is a similar function to convert back from network endianness to host local endianness. And so long as you always convert to and from the convention, the network byte ordering, well, then you don't need to worry about any differences between the endianness of the transmitter and the receiver. Right, so the next function down then, that's this fetch method. And all this does is to take a URL and do a GET request on it. So we pass in the URL as a variable, and eventually we get to this point in the code where we do a GET request on that URL and send back whatever response we receive using the send function that we just looked at. Now, whilst that's going on, we're also going to turn our LED on here and then turn it off at the bottom of the function here. And that basically means that for the duration of this function, the LED is lit. So we have a visual indication every time we send data over the Wi-Fi network. So the next function then, well, that's called read message, and unsurprisingly it reads a message. So we begin by checking to see if there's any data to read. If there is, then we'll read 7 bytes of it, or at least 7 bytes of it, and that's the message header. And then we'll go ahead and verify that the message was indeed a valid message. We'll read back the size of the message, and then we'll go and read however many bytes that is from the UART. Once we've completed that, we just return that data with the 7 bytes of header removed. Right, so that brings us to the main loop function here, and all that does is to read a message, and if we got one back, we compare it to the word sleep. If it was in fact equal to sleep, then, well, we'll go to sleep. So we respond with OK. We then set our status GPIO pin low to tell the Pico that we're no longer available before we enter deep sleep. Now to enter deep sleep, we use this esp.deepsleep function. We pass the first parameter in as being the time that we'd like to sleep for. And of course, because we can't actually wake ourselves back up using the time system, we're just going to pass in 0, and that means sleep forever. And the second parameter describes the mode that we'd like the ESP8266 chip to be in when it wakes back up. And here we're just going to return to the default mode. Right, so alternatively, if this wasn't a sleep message, then we just assume that whatever's in the message is a URL, and we call our fetch function here to do a GET request. And that's all there is to things on the ESP01 side. So, now it's time to take a look at the MicroPython program that's going to be running on our Pico. So we'll start with the necessary imports here, then we'll build the UART interface, and that's the same as in our previous version of this program. Of course, we're using the agreed baud rate. And the next thing we need to build is this ready object here. And this is bound to GPIO pin number 3, and it's set as an input pin because we're going to be using this to check the ready status of the ESP01. So once that's set up, we then build this reset object, and that's mapped to GPIO pin number 2. And this is connected to the reset pin of the ESP01 so that we can wake it back up from deep sleep. Now, under normal operating conditions, that pin needs to be held high, so we go ahead and do that here on line 9. Right, so now we encounter our first function, and this send message function here, well, this is a combination of the send function and the read message function that we've just looked at in the C program. So first of all, here's the send message part. Well, we're just going to write over our UART the data that we want to send in the message format. So we write MSG, then we write the size of the message body, followed by the message body. Now, this struct.pack stuff here, this is basically a Python mechanism for packing a value, in this case it's the length of the message, into an array of bytes that we can use to send over something like our UART interface. Now, the format string here, which controls how that message is packed, well, that says exclamation mark and then capital I. So capital I means unsigned integer, and the exclamation mark here, that means please convert to network byte ordering. So this is basically the Python way of saying network to host long. Right, so once we've written that out, we then go into a loop where we expect to receive a response. And this is very similar to what we were doing in the C program. We just read at least 7 bytes of data to ensure that we have a header. Then we check that the header is valid before reading out the size of the message. And then finally, we go ahead and read all of the data. And then we return whatever we read with the 7 bytes of header removed. So the next function along then, that's this ESP01 ready function, and what this does is it's basically waiting for the ESP01 to indicate that it's ready. So we have this loop here, and this basically says while the ready value is low, equal to 0, just wait. So when the ready value becomes high, that means the ESP01 has pulled its GPIO pin high, so it's saying it's ready to go. Once that's done, we just flush the UART in case there's any old stuff in there that we're not interested in. Alright, so the next function down from that then is Esp01 Sleep, and as you might imagine, this is used to send the sleep message, and that's really all it does. We just send the message sleep, and then wait for the Esp01 to set its status GPIO pin low to indicate that it has actually gone to sleep before we print OK and return. And if we can send it to sleep, well, we need to wake it back up again. And that's what this function does. And this is done by simply setting the reset pin low, then waiting for a bit, and setting the reset pin high. And that low to high transition will trigger the ESP01 to wake back up. At that point, we then call our ESP01 ready function, because the startup sequence for waking back up is basically the same as the sequence when the ESP01 first powers up, so we'll just use the same function to wait for it to become ready. Alright, so now we enter the main loop of our program. Basically, we'll just wait for the ESP01 to be ready, and that's for the power up sequence. Then we enter a loop here, and then we send a message containing this URL. And this IP address here is actually the address of my local Raspberry Pi workstation. So in a moment, I'll be running a web server on that, and we'll see the Raspberry Pi Pico contacting it via the ESP01. So once we've sent that message and received our response, well, then we just put the ESP01 to sleep, We wait for a little bit, and then we wake it back up again before beginning the loop all over again. So this proves that we can put the board to sleep, wake it back up, and use it to send messages. Right, that's enough explanation. Let's see if this actually works. So for the purposes of this test then, I'll be running a small local web server on my Raspberry Pi desktop, and here's what it looks like. It's very simple indeed. And what this does is it basically just serves out files from within whatever folder this web server is run from. Now within that folder, there's just a single file called index.html, and that contains the string hello from the internet. So, if everything goes to plan, the Raspberry Pi Pico will send a message to the Esp01 containing my IP address. The Esp01 will then contact the server running on my desktop, which will respond with this text message, and then that message will be sent back over the UART from the Esp01 to the Raspberry Pi Pico, which will print it out. So hopefully, this is what we'll see in our shell. Alright, let's give it a go. So I'll begin by connecting to my Pico and I'll run the software. So at the moment we're just waiting for the Esp01 to come online. Of course that won't happen until I power it up, so let's do that. Alright, great, so now we have our ready message, and that means we're in the first of these two sleep statements. And in a moment we'll send a message and hopefully get a response from the server. Ah, excellent, there we go. So here's our hello from the internet. Brilliant, so this all worked exactly as we'd hoped. Lovely. So now the board has been put to sleep and woken back up again, and now it reports that it's ready. So in a moment we'll send another message. Great, and there we are, we have our response again. So now I'm just going to change the contents of that index.html file, and we should see that we get a different message printed out here. So instead of hello from the internet, let's say, woo, this works. Right, let's see what we get back now. Excellent, so there we are, we have our new message. So as you can see, this is dynamically contacting that web server and issuing a GET request. Everything is working exactly as we'd hoped. Now to demonstrate that the Esp8266 chip is actually entering its deep sleep mode, we can take a look at my desktop supply here, because this supply has a little readout on it which tells us the amount of current that's being drawn. Now, this will only show to the nearest milliamp, and because the Esp01 in deep sleep mode draws less than a milliamp, well, the current will drop to 0, but of course it is still using some power. Anyway, that shows quite nicely that deep sleep is also working exactly as we intended. Well, there you go then. We've successfully Wi-Fi enabled our Raspberry Pi Pico in a much more useful and usable way than the little demo that we ended up with after the first part of this video. Now, as a bonus, we've also enabled the Esp8266's deep sleep mode to save ourselves a bunch of power, and that could be very useful if you want to use this in a IoT device that's powered by battery. So anyway, hopefully this has been interesting and maybe even useful. Thank you for watching, and I'll see you next time.